My name is Alex Bull, and I'll be introducing a report I wrote and that was published earlier this year by the Digital Preservation Coalition. That's an outline of the talk, but I don't really... No, go away. Don't really have too much time to dwell on that, so I'll leap straight into my introduction and say that I work for the Digital Curation Centre. Has anybody here not heard of the Digital Curation Centre? You've all heard of us. Great, that's fantastic. I can skip that bit. So I was first introduced to the challenges of preserving computer-aided design in a project called KIM, which was a Grand Challenge project that was co-funded by the EPSRC and ESRC. It involved 11 different universities and industrial collaborators from aerospace, defence and construction. We were looking at the challenges of firms providing their products as services. So we were looking at issues such as information organisation, selection policies for data, and finding ways of learning design lessons from in-service data and knowledge. Subsequently, I co-wrote a report on data curation in engineering disciplines as part of the DCC SCARP project. That stood for Sharing, Curation, Reuse and Preservation, but we had to swap the letters around so it didn't make an embarrassing acronym. And subsequent to that, I was involved in 2 JISC-funded projects that was looking at research data management within the University of Bath's Mechanical Engineering Department. So when the DPC asked me to write this Technology and Watch report on preserving CAD, it was quite an honour. I hope none of this will be too basic for those of you here present. It was a great opportunity for me to see how CAD was being used outside the mechanical and aerospace engineering context where I've been doing most of my work. Because when you start looking at it, CAD's being used in all sorts of different places. Originally it was little more than an electronic pencil for helping designers and architects produce their 2D design drawings of products and of buildings. But archaeologists then found it a very helpful format for being able to produce their archaeological site records. But then CAD really came into its own when it started being used for 3D models, both for products and for architectural designs. And again, it was also found useful for archaeological context, for producing reconstructions and 3-dimensional artistic impressions of ruined buildings. If you've ever seen a documentary on Channel 4 that had an archaeological element, you probably have seen one of these. It's CAD's also used in the entertainment industry for creating the virtual worlds that underlie many different computer games and as the way of creating 3D animations for films. And for people who are coming back to old CAD models, they tend to be wanting to do one of 3 things. They'll either be wanting to look up what the CAD models actually say. They'll be asking why the model turned out the way it did, or they'll be adapting it for a new purpose. And there was an initiative called Sustaining Engineering Informatics, and they characterised these 3 use cases as 3 R's of reference, rationale, and reuse. So for the next part of the talk, I'll be going through and looking at those in more detail. But before I do, just a quick note about why we should be interested in preserving CAD models. When you're doing the architectural models, at least things like hospitals, schools, skyscrapers and so on, they're built to last and with care can last for centuries. But the CAD models on which they're designed are most likely going to become obsolete within the space of about 10 years. So far we've been managing with paper plans and physical models, but as things get more complicated, as shapes become more organic, that's going to change. The engineering sector has already gone through this. Aircraft carriers and locomotives, they may not be in active service for centuries, but they still last a long time, much longer than the CAD systems on which they were designed. And we're already at the point at which the paper printouts just aren't expressive enough. Furthermore, you can't redesign from the paper plans. You can't manufacture from them because the computer numeric controlled machines are set up to work from the 3D CAD models. And the printouts tell you very little about why something was designed in a particular way. That kind of information is locked away in things like the design history, which only the CAD system can tell you. As I say, that CAD system won't be there in 10 years' time. Actually, it's not just the CAD system that we need to worry about, because CAD models are used as an input for a variety of other systems. I've already mentioned manufacturing systems, but there's also finite element analysis systems, geographic information systems, CGI renderers and ray tracers. With all of these systems relying on CAD models, it's important to consider how we can preserve them. Now, as the first speaker already said, there are no easy answers, no complete solutions. So what we have to do is always identify the aspects of a model that we're most interested in and concentrate on preserving those. So there might be situations where you're only interested in the final form of the model, in what we call the shape data. Here are a few examples of such situations. Companies like BAE Systems, Rolls-Royce, Balfour Beatty, they're now starting to provide their products as services. So it's in their interests to make those products easier to maintain. So if maintenance crews can tell them exactly where and what the issues are with the product or the aspect of built environment with reference to the original plans, they can improve future designs. It's standard practice to show a customer a artistic impression of a design for their approval, and admittedly currently that's mainly an analog use case, but with emerging technologies like augmented reality, we're beginning to see electronic versions of this becoming more and more useful. On big engineering projects, you will often find different companies working on different bits of the product. The lead contractor has to make sure all the different bits join up, but the companies don't necessarily want to give each other full access to their own designs in case one of their collaborators ends up stealing that design from them in a future contract. So they would rather just share the shape data. And if all you need is the shape data, then probably the safest thing to do is export the CAD model to a lightweight visualization format. These tend to be very simple, so there's not that much that can go wrong, and they're also tend to be rather compact, so they're easier to store and easier to move around. There are some examples of lightweight formats there on the slide. The ones on the left, X3D and U3D, are both standard formats. The ones on the right are proprietary. Well, the HSF is a bit of a funny one. But the proprietary ones, because they're controlled by a single commercial company, the long-term sustainability of that is somewhat questionable. But when products are in service a long time, things wear out, things get damaged, and if you don't have a spare, you need to make a new one. For this, you need more than just the shape data. You also need product manufacturing information like geometric dimensions and tolerances. There are lightweight formats that can store that information as well. JT is an ISO standard that's commonly used in aerospace and the automotive industry. Précis is something that is a format that's about to become an ISO standard, and that's used extensively in 3D PDFs. IGES was withdrawn as a standard quite some time ago, but many systems still support it, although they do tend to choose which parts of the specification they support, and the bits they support vary between different systems, so it's not always easy to know if if two systems are both supporting the same part. I have a couple of real-life examples of use case, and one of those is this. What you're looking at here is a model of the rear case of a television. The manufacturer, Philips, would never really need to edit that, but they might reuse it for a number of different models. So JT is actually a very good format for them because they can manufacture it from them, and they can use it as reference when they're designing a new set of innards. And what you're seeing there is the JT model embedded within a collaboration and archiving system developed for them by the European Shaman project. But sometimes the what isn't enough. You also need to know the why. If a plane crashes or a building collapses, investigators have to determine what went wrong. Was the plane sabotaged? Was it poorly maintained? Was there a fundamental flaw in the design? Uncovering that flaw is important so that they can make sure that any other products or buildings that use the same design are either taken out of service or made safe again, and also to make sure that that's never included in a future design. And uncovering that flaw requires access to the original design documents. A rather more common scenario is tied to reuse. There was a company I know of that was scaling up operations, so they had to set up some more factories. And obeying the maxim of, if it isn't broke, don't fix it, they simply transplanted the machine, cabling and pipework design from their first factory to all of their new ones. But the buildings themselves weren't identical. The new ones didn't have so many internal pillars for a start. So once they'd installed all of their machines and their pipework and everything, they found that the pipes were taking some very odd routes in order to avoid pillars that weren't there. The lesson there is if you're reusing a design, you need to know which requirement or constraint prompted a given decision. From an academic perspective, it can be interesting to know how a design was built up. Did the architect start from the outside and work in, or from the inside and work out? One source of evidence that you can use for answering these sort of questions is the construction history of the CAD model. Construction history modelling is a bit like the ultimate undo button in that it records all the steps that went into the design, and you can also insert extra steps and see the effect that it would have. Perhaps even more useful is feature-based modelling. Features explicitly record the engineering significance of certain shapes in a design. So if you have a curved blend between two surfaces, that might anticipate a construction process, or it might be there to remove a concentration of stress. The feature semantics would tell you which was the intended purpose. But incidentally, that kind of thing can cause conflicts. On the screen there is a idealized version of a plane wing. The designer might need this marked up as ribs that have been applied to a base surface in order to calculate the optimum distribution. But a manufacturing engineer might need it marked up as cavities that have been milled out of a thicker surface. It's not usually possible to have both of these in the same model. Now, the lightweight models I mentioned earlier won't contain that sort of information. You'd either need the full native file formats used by the CAD systems themselves, or a full exchange format such as DXF or STEP. DXF has a published specification, and it's supposed to be able to express all of the information that's encoded by AutoCAD's native DWG format. But by all accounts, recent specifications have not been detailed enough for full support to be implemented in third-party tools. STEP, ISO 10303, has pretty much the opposite problem. It's been in continuous development for the past 30 years, and at 600 parts it's the largest ISO standard. So that's an awful lot of documentation to get through. And within that standard there are various ways of expressing CAD data. Most CAD systems support AP203 edition 1, which is quite old. It was quite basic. But there is now an edition 2 of that part, and there's another part, AP214, which extends support in a different direction. And soon there will be AP242, which will supersede both of them. Now, there are some vendors who are working on supporting all of these standards, and even the forthcoming AP242 through something called the CAX Implementer Forum. And that does bode well for the future. And it's worth noting also that STEP is the basis of many other international standards, such as the industry foundation classes for building information models, though I think it's fair to say it's still very early days for IFC. There are, however, some other ways of recording rationale outside of CAD models. In the KIM project, the team at Cambridge, in collaboration with Rolls-Royce, developed a tool called DREAD, the Design Rationale Editor, which built on an earlier idea known as the Graphical Issue-Based Information System. This is an example of a DREAD map, and it shows how a particular design issue was solved. The map contains hyperlinks, so you can jump back and forwards between other rationale maps, and also reports or spreadsheets or even design documents. When a customer's requirements change, this usually means that the design needs to be tweaked. In addition to the techniques I've already mentioned, CAD systems have some other capabilities that can make editing an existing design easier. Parametric modelling helps to automate the editing process, so aspects of the design are made to depend on parameters, and constraints are added so the computer knows how to adjust things should those parameters change. Procedural modelling is where algorithms are used not only to automate repetitive tasks, but to give surfaces fine texture, to create realistic snowdrifts, or to generate entire cityscapes from a single building. It's used extensively in the creation of virtual worlds, but it's also started to be used in serious design work for creating intelligent parametric features, for generating intricate structural patterns, and for finding optimal architectural forms. CAD systems also provide mechanisms for including the same part many times in an assembly. So if you need to edit that part, you only need to do it once, and the change propagates throughout the entire design. The same mechanism can also be used to make a design modular, so that parts can be swapped in and out as optional extras. So some CAD systems have a library of standard parts, like doors, windows, staircases, and they're preloaded with feature semantics and parametric properties. If those parts are hard-coded into the software, it can be very difficult to represent them reliably in a different system. Alternatively, the parts might be saved as separate CAD files and included in an assembly by reference. That does make them more portable, but it does require keeping track of multiple files and preserving the links between them. For the sort of lower end of the CAD market, they would do that by using relative path names, but for the more advanced systems, they tend to rely on using IDs that are managed by a central register, and that would be either by the building information model system, or in industrial engineering they use a product lifecycle management system. These systems also manage the relationships between CAD files and the other types of data and models that are used by designers, and handle access control. Preservation systems might have to be able to do the same thing themselves. The idea of reusing parts in assembly is actually quite commonly supported, though as I mentioned, that there is that problem if part libraries are differing between systems. But visualization formats typically don't include parametric information. STEP can support parametric models, but as far as I know, it hasn't standardized procedural modeling yet. Indeed, because such a variety of programming languages are used, there's hardly any interoperability in this area at the moment. So that was a quick look at some of the types of information that can be found in CAD models and how widely they're typically supported. So in the time that's remaining to me, I'd just like to go over some of the options that are available to people who are having to preserve CAD models. Now, as I said, there is information that can only be held by the original CAD model. And if you are just preserving that original CAD model, it does make guaranteeing the provenance of it rather easier. But there is the other problem that in 10 years you won't be able to read it unless you engage in some sort of software preservation, for example, by creating an emulation platform for preserving the original CAD software. But even that has issues, because as the system becomes more and more out of date. There'll be fewer people around who know how to use it. And if you ever need to reuse that CAD model in a different system, you'll be stuck because you'll only be able to read it in that one CAD system, and the newer systems won't be able to read the CAD format. So another approach you might take is to continually try and upgrade and migrate these CAD models to the latest CAD formats. But every time you do that, there's a risk of losing some information, and at some point you're going to have to migrate from one system to a completely different system, and you're looking at major data loss there. So a way of limiting that kind of damage is to take a normalisation approach, which differs from the first one in that whenever you're retrieving a model out of the archive, it'll only ever been migrated twice. Once when it went into the archive, into the normalised format, and once when it comes out, it's been translated into the format that you can read. There is, which means that you're going to be getting more of the original data, but you still need to know what information you're missing. And you need to be able to check to see whether any of the information's got corrupted in that migration process. So there's a way of checking that, and that's to use a validation system. There's a project in aerospace called LOTAR that have been looking at these sorts of issues. So, for example, for shape data, what they recommend doing is in the original CAD model, creating a cloud of points, sets of coordinates that trace out where the surfaces are, where the edges are, where the vertices are. And what you can then do is when you're load the model into a new system, you can overlay that set of coordinates. And if the coordinates all match, you know the shape data has been preserved correctly. And if there are points that are just in the middle of space, you know something's gone wrong. There are some other things that you need to bear in mind when you're preserving CAD. Supporting documentation is absolutely essential for maintaining understanding of the CAD model, even if it's not technically needed for support for being able to create realistic renderings of the CAD models themselves. So, for example, it's useful to know if somebody has been creating their architectural model in compliance with the US National CAD standard, which will then tell you what all the layer naming conventions were. In order to preserve more of the rationale information, things like the client's original specification can come in very handy, and the kind of rationale models that I showed you earlier, such as the ones created by Dredd. And if you're seeking to preserve procedural model algorithms, one thing that you can do is make sure that when you have the procedural script, that it's fully documented, annotated with comments, so that gives you a greater ability to be able to reproduce that in a new system. So, just some final thoughts to wrap up then. CAD files can be used for many different purposes. So it's important for an archive to establish why models are being kept and use that as the basis for deciding a preservation strategy. If particular properties are important, create validation tests that can prove whether or not they've survived. Because there is information that cannot be exported from native CAD formats, they may as well be preserved for as long as they're readable, but since they will be unreadable one day, they should also be normalised to a full exchange standard-like step and to a visualisation format for backup. It's important not to neglect supporting documentation, which can be vital for future users to be able to understand the models. And finally, if we are serious about preserving CAD models, we need to impress on regulatory bodies and CAD vendors how important support for these open standards is. Because the information that's locked up in CAD models is too valuable for its survival to be left in the hands of a single corporation whose interests may lie elsewhere. It needs to be put into an open standard format where it can be exchanged and preserved for the benefit of its creators and society as a whole. Thank you very much.